Hello, my name is Richard Castillo and I am a student at Lone Star College Kingwood campus, and I'm going to be making a video explaining these problems, how to solve them in Chem 1412. First off, we need to find the highest. This is chapter 10, question 43 of the EOC. First of all, we need to find the highest boiling point between HBr, Kr, and CO2. Now, looking at HBr, we draw the small little structure for it. Bromine has an electronegativity of 2.96, whereas hydrogen has an electronegativity of 2.18. Now, since bromine is more electronegative than hydrogen, it actually pulls the hydrogen towards it, giving the bromine a partial negative charge and the hydrogen a partial positive charge. Now, if we were to put another substance of the same hydrogen and bromine next to it, and we know that hydrogen has, of course, the partial positive charge and bromine has the partial negative charge. Since the bromine and hydrogen are the opposite charges, they are attracted to each other, which is an example of the dipole intermolecular force. Now, krypton and CO2 both have a single element substances, making them only have London dispersion forces. And since they only have London dispersion forces, whereas HBr has dipole-dipole, it's the stronger the intermolecular forces, means the higher the boiling point, making HBr the higher boiling point. Let's look at the highest freezing point between H2O, NaCl, and HF. Now, if we look at H2O, NaCl, and HF, we notice that H2O and HF both exhibit H bonds. If a hydrogen is connected to an oxygen, nitrogen, or fluorine, then it exhibits the H bonds. So we know that these two have H bonds. Now, sodium chloride, on the other hand, exhibits an ion-ion intermolecular force. And since ion-ion intermolecular forces are stronger than H-bond intermolecular forces, that makes sodium chloride the higher freezing point. Now we need to look at the lower vapor pressure at 25 degrees Celsius between CO2, Br2, and I2. Now, looking at CO2, Br2, and I2, we notice that these are all single element intermolecular forces. Now, it's all single element London dispersion forces. Now, how do we determine which one has the weaker London dispersion force? Well, or the stronger? If we look at the periodic table, we notice that iodine is the lowest between all of them, between bromine and chlorine, which makes it the larger molecule. And since it's the bigger molecule, that means it has the stronger London dispersion forces, which makes the vapor pressure the lowest at 25 degrees Celsius. So I2 is the lower vapor pressure at 25 degrees Celsius. Next, we need to find the lowest freezing point of N2, CO, and CO2. Now, N2, we notice, is a single element substance, making it only have London dispersion forces. Looking at CO and CO2, we see that if we were to find the electronegativity between them, C has an electronegativity of 2.55, and oxygen has an electronegativity of 3.44. Now, since C has the least electronegativity, it pulls the oxygen towards it, giving the C the partial negative charge and the oxygen the partial positive charge. So we have the partial positive charge, partial negative, partial positive. Now, if we were to write again, same as part A, if we were to put the same atom close to each other, we would notice that both of these have dipole-dipole moments or dipole-dipole interactions. N2 is London dispersion forces, making it the weaker intermolecular force, which in turn makes its freezing point lower than the rest. Next, we need to figure out the boiling point between CH4, CH3, CH3, and CH3, CH2, CH3. So, looking at these, we know that they all have London dispersion forces, of course. Every single substance has London dispersion forces. But since CH4 is the smaller molecule between all of them, we know that the weaker the molecule, the weaker the molecule, the weaker the London dispersion forces, which makes the boiling point in CH4 the lowest. Next, we need to look at the highest boiling point between HF, HCl, and HBr. Now, we know that HF, and then we got HCl and HBr. Now, looking at HF, we know that a bond between hydrogen and fluorine means that it's an H bond. Now we look at H and Cl. H has an electronegativity of 2.18. Chlorine has an electronegativity of 3.16. Same over here, 2.18. And bromine has an electronegativity of 2.96. That means the hydrogen atom is pulled by both the chlorine in this substance and the bromine in this substance, giving the bromine and chlorine the partial negative charge, and the hydrogen the partial positive charge. So if we were to finish this up, then we know that these both would be examples of dipole-dipole interactions. And since we know that hydrogen bonds are stronger than dipole-dipole interactions, that means the intermolecular force in HF is stronger than HCl and HBr, giving it the highest boiling point. Next, we need to find the lower vapor pressure at 25 degrees Celsius for CH3, CH2, CH3, OCH3, CCH3, and CH3, CH2, CH2OH. Now, each of these two exhibit dipole-dipole interactions, but CH3, CH2, CH2OH, in the atom, we can actually identify that the O is bonded to the H, which makes this substance have an H bond, which is stronger than dipole-dipole forces, giving it the lower vapor pressure at 25 degrees Celsius. Next, we have Chapter 9, Question 93. We have this, computer-generated model of caffeine. Now, this is the Lewis structure for this model, and these are the questions. We have to ask ourselves, how many central C and N atoms exhibit 120 degree bond angles? Now, these are all of the S and C, these are all the C and N bonds which exhibit a trigonal planar, which is 120 degree bond angles between all of them. And in the Lewis structure, we can see 6 of them. There are 6 sp2 hybridized atoms in here, and they show that each of the 3C bonded to the 3H, which is right here, right here, and right here, and each of the 3 N's bonded to the 3 C's, which is this one, and this one. So that means we have 6 sp2 hybridized atoms. We don't have any sp hybridized atoms. Now we need to find how many sigma and pi bonds there are. Each sigma bond is each bond between each atom. If we were to count all of the bonds between each atom, we would have 25 sigma bonds. The pi bonds are every single double bonded atom, and since we only have 1, 2, 3, and 4, that means we have 4 pi bonds. Next, we move on to chapter 10, question 101. Now, we know that the energy required to convert 0.500 kilograms of ice at negative 20 degrees Celsius to steam at 250 degrees Celsius. We need to find the specific, we are given the specific heat capacities of each, and here's all the information we need. So first, if we were to convert that 0.500 kilograms 2 grams, it would be 500 grams. So we know we have 500 grams. We need to draw the table to show each of these. So we have a temperature at -20 and the max temperature at 250. Next, we need to find the more common temperatures at each. We have 0 degrees Celsius, which is the freezing point, and 100 degrees Celsius, which is the boiling point. Now, we need to find from 20 degrees Celsius all the way to 250. To do that, we have to show the relation like this. Now, at -20 degrees Celsius, we know it's in solid form. At 0 degrees Celsius, still a solid. We need to undergo a phase change, making this the liquid form. It's still a liquid up here. Undergo a gas change to turn this into gas, and still a gas up here. Now, this is the specific heat, Q1. This is Q2, Q3, Q4, and Q5. Now, Q1, Q3, and Q5 are all temp changes. Q2 and Q4 are both phase changes. Alright, so now to find the temperature changes of Q1, Q3, and Q5, we need to use the formula Q is equal to M cat. Now, in Q, to figure out Q1, we need to figure the mass. Of course, we have 500 grams. And next, we need to find the temperature in which the state is a solid, which if we look up here at our specific heat temperatures, we know that if it's in a state of solid, it is 2.03 joules per grams degrees Celsius. Next, we need to multiply by the temperature, the change in temperature, delta T, which is 0 minus -20 degrees Celsius. Now, whenever we input all this into the calculator, we will get 20,200 joules, which converts to 20.2 kilojoules. Next, we need to find the formula for Q2. Now, Q2 is a phase change for which we had to use a different formula. This formula is the N times delta of the process. Now, in Q2, we know that we have 500, that's the mass, over 500 grams over 18 grams per mole, because we need to figure out the moles for it. And then we need to multiply that by the phase change of this, which is which we are given up here in fusion, which is 6.02 kilojoules. Sorry, 6.02 kilojoules per mole. So if we were to input all this into the calculator, then we would get kilojoules of 167.22 kilojoules. Next, we need to find Q3, which is also a temperature change. We have 500 grams, that's the mass, and we have the C, which is, if we look at the specific heat capacities, we know that it is 4.18 joules per grams degrees Celsius. And when the change in temperature is 100 minus 0, which is just 100. And if we were to input this onto the calculator, you would get 20,900 joules, which is just 209 kilojoules. Next, we need to find Q4, which is also a phase change, but we use a different, we use this formula for it. We do 500 grams divided by 18 grams per mole to find how many moles are this substance has. That And then we need to multiply that by 40.7, which is the directed phase change that we have to do. 40.7 kilojoules per mole. This gives it, if we were to input all this into the calculator, we get 1,130.56 kilojoules. Next, we need to find Q5, which is equal to another temperature change, which is 100. We need to find 100 grams, and then the phase in this, which in this is, which is 2.02 joules per gram degree Celsius, and the change in temperature is 250 minus 100 degrees Celsius. If we were to input all this into a calculator, you would get 30,300 joules, which is just 30.3 kilojoules. To find the Q total, you had to add up all your Q values, and if you were to add them all up, you would get a Q total of 1,557.28 kilojoules. The next question is chapter 10, question 107 of the EOC. Right here we have the phase diagram for carbon. This is the pressure. We have 0, 2,000, 4,000, 6,000, the graphite, diamond, liquid, and vapor. Now, we need to figure out how many triple points are in the phase diagram based on letter A. So we look at the triple points. This right here is a triple point, and right here where the 3 of them intersect is a triple point. So that means we have 2 triple points. Now, we need to figure out which phases coexist at each triple point. Now, at the higher vapor pressure triple point, which is this one, we have graphite, diamond, and liquid. Now, at the lower vapor pressure point, which is right here, we have graphite, liquid, and vapor. These two are each show the phases at which they coexist in the triple points. Next, we have letter C. What happens when graphite is subjected to high pressure at room temperature? Now, if graphite were to be subjected to high temperature, then high pressure, as we can tell, as pressure increases, graphite will turn into diamonds. So, if subjected to a higher pressure at room temperature, graphite will be converted into diamond. Next, we have letter D. If we assume density increases as pressure does, which is more dense, graphite or diamond? Well, diamond is more dense. Diamond is more dense than graphite, as we can see, given by the pressure. As pressure increases, density increases. So, diamond is more dense. Which is why graphite can be converted to diamond just by applying pressure. So that's why that is this question solved, and that's all 4 questions solved. I am Richard Castillo. Thank you for watching this video. Thank you.